הבעיה זה שהסטודנטים הפסיקו לבוא.
רגע, הוא לא התלונן שאני מקליט?
מי התלונן? יאללה. So, רגע, זה באנגלית או בעברית? באנגלית. So, hi, and I will give the talk about, you can't see it because of this bullshit. איך מורידים את זה?
אתה צריך במור, הולך למור בסוף.
כן. hide video panel.
hide floating meeting.
יופי. So, I will be speaking about xylem cavitation and how common it is in plants under natural environments. And today I kind of read the title that I gave at the time and I realized maybe it's a bit deceiving. So by natural environments, I want to distinguish what I'm about to show you from most experiments, which usually looks at xylem cavitation in potted plants or in growth chambers. So natural environments can be also man-made environments, like orchards, like man-made forests. Okay, it's not going to be. It's difficult to find in Israel something that it's actually natural. And most of the audience have already heard me speaking several times, so I'm not going to give the introduction that I usually do. But I realized that I do need to give some introduction about what is xylem cavitation, just to be specific. So xylem cavitation is because plants, xylem is the tissue that conducts water in plants. And because the water is conducted under tension, under negative pressure, because of the suction that the transpiration creates from above. So if you think about it from a thermodynamic perspective, xylem or water cannot be under negative pressure. Okay, they should be gas. And sometimes when the pressure becomes too low, they actually are transformed into gas. And it's a big problem for plants because if the pipes are full of gas, they no longer conduct sap. Okay, so if it's a small proportion of the pipes that no longer conduct sap, it's just damage the productivity of the plants or the potential productivity of the plants once you irrigate them, because it will take time until they will regrow new xylem. But if it's a large proportion of the xylem elements that are being clogged by gas, then the plant will die. And now I want to show you, just to show you how important cavitation it is, or at least how people think it's important.
What is cavitation? So important.
What is cavitation? Is the transformation from liquid to gas. Okay? Okay. No. So there's a lot of papers, and because it's the reality about tree mortality in recent years. Okay? And in fact, apparently, if you'll detect a large mortality event around the world, you'll probably make it to the best journals there is, because they love dying trees. And if you notice, most of these reports associated the mortality with climate change. You see, with climate warming, maybe I should do it with this. This is a mortality triggered by drought and temperature stress. This is another paper, Global Field Invasion. It tells you the drought, reveal hotter drought for fingerprint for Earth forests. So forests are dying at an increasing rate if you compare it to what's happened before. And it's associated with climate change. And if you go to all the recent reviews on why trees are dying, so probably one of the major trigger is xylem cavitation, hydraulic failure of the xylem. And you can see in the first one up here, you can't really see the title doesn't say it, but I read it and I can tell you it mostly speaks about cavitation. Here, tree mortality predicted from drought-induced vascular damage. This is a PNAS. All of these are excellent journals. Rapid hydraulic collapses cause for drought-induced mortality in conifers. So the fact is most people will argue that it's because of xylem cavitation. Now, the funny thing is that there's not really much evidence to support that it is cavitation under natural environments that kill trees. We can test it in pots, in the greenhouse or in the growth chamber. It's very difficult to measure cavitation out there. Okay, this is just an example for one of our measurements, how to know that cavitation took place. You take shoots from the forest, you perfuse it with dye, and you see up here. Up here, you can see that these are shoots that conduct the dye. That's why they become colored. And these are shoots that do not conduct the dye. So it means they lost their conductivity due to xylem cavitation. Okay, this is just a method for seeing if a tissue is conductive or not. And you can see that Arendt and co-authors, they made a correlation between how conductive or how active the xylem area is. This is the x-axis, to what is the foliage area that still exists on the shoot. This is after following a drought in Germany. Okay, this is a destructive method, so you can't really follow these shoots over time. You can't really know the dynamics, and also it's very laborious. You can't really do it every other day. It's simply not possible. So what happens is you normally go to the forest or to an orchard or whatever, and you detect trees that don't look so good, and you measure and you see they actually cavitated. And it's difficult to say if because they are dying, there's cavitation, or because of the cavitation, they are dying. To do that, you need to know the dynamics of the cavitation, exactly when it occurred, to show that cavitation occurred first, and only then the trees died. So the method which people do that is normally they construct a vulnerability curve. Okay, this is a vulnerability curve. It says how much % loss of conductivity you will have as a function of the xylem pressure. Okay, there's several methods to do that. This one is with a centrifuge. Basically, you take a shoot and you spin it really quickly, and because of the centrifugal force, in the center of the shoot, you will have negative pressure. So you can calculate what is the negative pressure, and then you measure the conductivity of that shoot, okay, by just perfusing a liquid through it and see how much liquid passed through. We have this centrifuge down here at the basement. Shabtai brought it at the time, and we frequently use it. Now that you have the vulnerability curve, you only follow the water potential. So you see here they followed the water potential through time. And when the water potential became negative, reaching the P12 or the P50, this is the water potential that will lead to 12% loss of conductivity or to 50% loss of conductivity. So when the water potential reached these values, these thresholds, so they assumed that you have a lot of cavitation, and you realize that the trees that really went down, they eventually died. These are Christian trees, so it's marked with a cross. It's in Germany. So this is probably the common procedure to know the dynamics of cavitation. Yes.
Just to understand, when xylem pressure is like -2, -1, still there's the full transformation of liquid to gas, but it had to be, because there is delay.
No, it's not delay. The liquid is metastable. All the plants that you see here outside are at
metastable. Still, it's not enough.
Yeah, it's most of the plants, if you go outside and measure them now in Israeli summer or spring, they will be at -1 megapascal, and they did not lose any conductivity.
It is just metastable, but it is supposed to be the
but they operate at a metastable state. It's always metastable. Okay, this is how plant
reduce much, apply much more negative pressure and then to fix it.
Yes. Okay, it's a specific mechanism which I will not go into.
Just the same what happens with evaporation of water from now force.
Okay. Okay. Yeah.
Just wanted to understand it exactly.
Okay. So there's a common assumption, or there's a hidden assumption in this analysis, and that is that P12 and P50 don't change over time, right? You measure it once and you assume it's always that way. Here I have another example. They measured, they have here a P50, the water potential that leads to 50% cavitation. It doesn't even work. Here it is. And they assume it didn't change over 2 seasons. You see, the first dry season, they didn't reach P50, the water potential. On the second dry season, they crossed P50 and they assumed that they had a lot of cavitation, okay? Now, there is some logic in assuming that the xylem vulnerability doesn't change through time because the xylem is a dead tissue. It's composed of dead cells. And if the cells are dead, you can assume that they're probably not very plastic. So that's probably what the hidden assumption behind the hidden assumption. And now I'm going to take you back to what I presented here in my last presentation a few years back. So this is basically in grapevines, this is the sequence of physiological responses to dehydration. So at the x-axis, you can see the leaf water potential, and in pink and in black, you can see the stomal conductance. So you see that when there is dehydration down to minus 1.2 megapascal, this is in grapevines, each species has its own values, there's stomal closure. Plants are trying to avoid dehydration. They try to conserve their water, they close their stomata. If they keep drying because some vapor is escaping through the cuticle or because other plants are taking the water or the soil evaporates, they reach turgor loss point and then they wilt. Yeah, the leaves are wilting, they become sad. And only after that, when you reach to lower values, there's a cavitation. And this is the vulnerability curve we constructed for grapevine leaves. And because we saw that first there's stomal closure and wilting, and only then there's embolism. And also we found in that paper that if there is embolism, the leaves will generally be shed in grapevines. So because we don't see that in real vineyards, it's very rare to see wilting, it's very rare to see a large leaf shedding. So we assume that there's no cavitation in vineyards, that it's not a common phenomena, even when you give them water deficit, okay? But I was kind of, so that was the assumption. I was kind of challenged by Ishai Netzer, yeah, my colleague and friend. And he was basically saying, look, he was using the former approach. He was saying, look, I take your vulnerability curves, I take your values, and I combine them with the water potential that I normally measure in vineyards. And I know I frequently get to values which are lower than minus 1.6 megapascal. You claim that at minus 1.6 megapascal there's cavitation. I measure minus 1.7, minus 1.8, and sometimes minus 2. So it means there's a lot of cavitation in vineyards, okay? So basically our hypothesis was, we had to guess why is he wrong? What's the problem with this contradiction? And we know, for example, about turgor loss point that it changed through time. It changed throughout the season. There's a lot of data about it. This is from Maria Mar Alcina. This is 8 different grapevine varieties. And she measured their osmotic potential at 0 turgor. It's basically when they lose turgor in May, in July, in August, and in September. And you can see that in May, it's at about minus 1.2 megapascal. And in July, it's minus 1.5 on average. In August, it's more than that. And in September, it's less. Yeah, it's more negative than minus 2. Now, if you think about it, sometimes grapevines are below minus 1.2 and below even minus 1.3. But it never happens in May. In May, it's a Mediterranean crop. There's a lot of water in the soil. In May, typically what we measure now is like 4 bars, minus 0.4. Okay, by the time the vines will reach minus 1.3, it will be August. And then there's also already osmotic adjustment. And in coordination with this osmotic adjustment, we just published earlier this year in collaboration with Jose Carlos Herrera, that there is a shift in stomal closure, okay? Basically, if you measure stomal closure, this is in potted vines, we allow them to dry while measuring their stomal conductance and water potential. So you see that in June, stomal closure occurs at minus 0.6. In July, full stomal closure is about minus 0.7 or something, and in September, it's later on. And this is in coordination with the osmotic adjustment and the shift in turgor loss point. As turgor loss point becomes more negative throughout the season, the water potential which leads to stomal closure is becoming also more negative. So plants can transpire more as the season progresses and as it becomes hotter and the soil becomes drier. Now, this is an argument that is easy to push. The scientific community will easily accept it. But Regarding xylem vulnerability, again, it's harder to push the idea that it's plastic, that it changed through time, because these are dead cells. This is, again, the sequence of plant response to dehydration. First, there's stomal closure, then there's tuber loss point, and only after there's cavitation. Now, we hypothesized that if the tuber loss point shifts throughout the season to more negative water potentials, and stomal conductance shifts throughout the season to more negative water potentials, so also the xylem vulnerability should move to more negative water potential. Otherwise, we would get this image, which doesn't make sense from a strategic point of view, that plants will transpire, keep their stomata open despite the fact they are cavitating. Because again, cavitation is irreversible. Even after you irrigate, it's debatable if they can refill. And in most cases, they will have to regrow new xylem, which takes a long time. So we assume that it changed. Jonathan was the student that had to show that it happens, and he did it in Shiloh. Basically, you see the development of the canopy, and then you can see that during the season, the vines dehydrated from 0.4 bars to 0 megapascal down to minus 1.3. He measured the solute accumulation. So you see that solute throughout the season almost doubled itself from 300 millimoles per kg up to 700 millimoles. And accordingly, turbo loss points have also declined from minus 0.8 megapascals to minus 1.8. So throughout the season, the plants are accumulating osmolytes, and that's why their turbo loss point is shifting. He also did lab dehydration trials, okay? And I'm not gonna explain exactly our optical vulnerability method. It means he brought shoots to the lab, and he allowed them to dry while constantly imaging them. And because gas bubbles change the refraction of light, so if you constantly image the leaf, you can see the propagation of embolism. I explained it. I think most of the audience have seen this method before, so I'm not going to go into details about it, but you can ask me later. And what he found that in May, stomal closure occurs until 11 bars, okay, and only after cavitation starts. When he did the same thing in July, there was a shift of about 3 bars. Stomal closure occurred completely at 14 bars. This is turbo loss point, and only after cavitation started. And in September, it happened even 3 bars later. Stomal closure occurs at 18 bars and only after cavitation started. Okay, so first we showed that in grapevines, and I think you've seen this, some of you have seen this before. You'll hear the part that we already published. Now, we wanted to show that it kind of makes sense that the leaf of a deciduous species, kind of like grapes, will shift throughout the season, okay? Because their whole life extent is about 4 months. We wanted to see if it will happen in forestries, things that are less plastic, and we checked it in Pinus halepensis, what we call Jerusalem pines. This is the work of Dr. Funk that just sadly left us to Austria, to a better position. And what she found is basically, if you can see here, that this is the water potential up here. Okay, and the water potential starts high in March. This is March 2020, for the end of the rain season, and then it declines until October. Then it goes up again, and then it declines again and goes up again. Okay, this is the fluctuation of the known fluctuation of the stem water potential through our Mediterranean climate. The interesting thing is also that turbo loss point shifts together with the water potential and also the P50. The water potential that leads to 50% cavitation, it changed throughout the season. It started at about -3 and it declined to about -4. Okay, and then it increased again to -3 and declined again to -4. She did it for 2 years. Okay, these are just the climatic data for those that are less familiar with the Mediterranean. Now, if we would have taken the common procedure of measuring the cavitation at one point in time, and normally, by the way, this one point in time will be in winter. For methodological reasons, it's better to measure these stems when they are hydrated. So if we would take our measurement, the first measurement we did, and just think the P50 doesn't change, like the papers I showed you earlier, then we would get almost 50% cavitation at peak summer, okay? Clearly, this is this is not the case because the P50 changed as well. And I can show you that there was actually no cavitation, not only based on this estimation, but we also took some branches to the lab and we did micro CT. So in micro CT, everything that is dark is air spaces, and everything that is kind of gray is still full of liquid. So you can see some air spaces here in the pith, and you can see some air spaces in the bark, and some air spaces in the xylem. Okay, but when we quantified it, it was 3 to 5% of the xylem area. So it's very, very marginal amounts of cavitation. Nothing like what could have been suggested by checking a constant P50. Okay, so this is Pinus alepensis. Also, Jonathan, which I showed you his grapevine experiments, he wanted to do it with other deciduous species to see if it's true for all deciduous species or if it's something unique to grapevines.
Only 50% of the cross-section is
No, it's important then. Important question. P50 is the water potential that will lead to 50% loss of conductivity. Okay, so this is a water potential value. When you make a vulnerability curve early in the season in March, then the P50 will be -3. -3, they will lose half of their conductivity. But when you do it again in October, it will be only at -4. You have to dry them 1 megapascal more for them to lose the same amount of conductivity. Okay, meaning that their that the initiation of cavitation is it's not reached here. We use P50 because it's more standard than using P1. Also, statistically, it's very difficult to know when is the first % of the cavitation.
Oh, that I understand, but what's the relation between the cross-section and area that you showed there?
Yeah, so
cavitation and
it's this. So it's arguable, but to make it simple, 50% loss of area would be 50% loss of conductivity. Okay.
And this will be reached at different water potentials throughout the season.
Yes. Yes.
Only because of the solution osmolyte change?
No. It has nothing to do with the solid osmolyte. So the osmolyte change, it drives the turbo loss point. It drives this side. Okay. So turbo loss point, it's a well-known phenomenon that plants under stress, they accumulate osmolytes, and then they can sustain their turgor under drier environments. Okay, it's at least 50 years. It's more than 50 years old known knowledge. The shift in xylem vulnerability is less explored. Okay, that's what I'm showing you today. And if you
reach the mechanism,
the mechanism? Oh no, I don't know the mechanism. I can only hypothesize, but I will. Okay. We don't know the mechanism yet. Okay, to be honest. Right. Jonathan did it with 9 deciduous species. Okay, Serkis is a Judas plant, Klila choresh, Pyrus pear, agas, punica is pomegranate. Okay, so they're all growing here on campus. This is the pomegranates that grow back in the institute. Everything grows here on campus. The ones in yellow are Mediterranean or temperate species. The one in green are all kinds of deciduous species that grow here on campus, but they are ornamental and they come from tropical or subtropical native habitats. Okay, we just randomly selected them, but only later we realized we have to classify them from where they are coming from. So what you can see basically is that the ones that are in yellow, the Mediterranean or temperate, the ones that are coming from areas that change their environment throughout the season, they change their P50 throughout the season. Even though everyone grows here in the Bet Dagan campus, yeah, with the same climate. So you can see that the P50 goes down here and it goes down here. Here it's less clear, but eventually it went down. In the pomegranate appear to be very, very resistant species. You see at the end of the season, they cavitate only at -6 megapascal. They reach 50% cavitation. So 4 out of 4 change their P50. When it comes to the tropical or subtropical species, only 2 out of 5 change their xylem vulnerability throughout the season. And also, so again, I'm showing you here that, again, if I would have taken the P12 and assumed it not to change throughout the season, I would get to cavitating values. Okay, so it's just I think it's a bias to look at one point of the season and assume it's valid for the whole season. We made a comparison between the Mediterranean or temperate species and the tropical or subtropical species, and we realized that in the Mediterranean or temperate, there's a larger change in the turbo loss point throughout the season, and a much, much larger change in the P12 and P15, the xylem vulnerability. And again, they are all growing in the same climate, different genetics, but it's the same conditions. And something I wanna maybe raise a thought, I don't know if it's the real answer, but Choate, he made this large analysis of where cavitation occurs, okay? He quantified cavitation by comparing the xylem vulnerability of species and the P50 and the water potential, the lowest water potential that was measured for, I don't know, several hundred species. And he realized that, you see, this is he calls it safety margin psi 88. It means it's the difference between the water potential and the 88% cavitation. Dots that are below this line are trees that supposedly got 88% loss of conductivity or more than that. And you realize it only happens in the Mediterranean. When you look at tropical or seasonal forest or tropical rainforest, it doesn't happen. And it could be that it's because of this bias. And the bias mostly we see exists in environments which change their climatic conditions. Okay, I don't know if this is the case, but it's just a thought that I wanted to share. We have time. Okay, I don't have much more. Now I showed you this paper before, where we showed that turbo loss point also drive a change in stomal conductance. In this same question, we also ran a model to ask a question. So what's the advantage of this adjustment, of this seasonal adjustment? What is it good for plants? And basically, intuitively, you're saying that if plants can go to lower water potential, it's probably good for them to explore more of the soil, right? To get more water out of the soil. And what we found is actually that if you look at it in terms of water potential. So in red, it's with no osmotic adjustment. It's plants, again, in a model that cannot make osmotic adjustment or P50 adjustment. And you see that at 0.4, that's what they're reaching the end of the season. If there is osmotic adjustment, they can make it to 0.5. But if you consider the amount of water which they get, and we model real plants with real root volume, I don't know, like 2 cubic meters or something like that. It's not a lot of water. If you consider that you are a soil scientist, if you consider the retention curve of soils, there's not much of a difference between a 0.4 megapascal and 0.5 megapascal. It's about 1% or something like that increase. If you consider it in time, this is the day of year. So this is more or less the grape growth season. So you realize that it actually means that they reach critical stomal conductance, the values of stomal conductance, which they can no longer assimilate carbon. They are actually become negative in assimilation. It happens faster. It happens about 10 days earlier because they transpire more in the early season, and then they deplete the soil water content. So what is it good for anyhow? I mean, not all, but many plants are doing that. So it's gotta have an advantage. So one possibility is that it's good for environments in which you have some sporadic rain events, okay? If you have, for example, weekly irrigation, or it doesn't matter, bi-monthly precipitation or whatever, it's really an advantage if you have osmotic adjustment, and it means that throughout the season, you can open your stomata more. And I can tell you that the grape, for example, the stomal conductance increase through time. In May, it's relatively low, and you compare it to June, it's more, and in July, it's even higher, typically, okay? And the advantage is even clearer if you also increase the temperature of the atmosphere. So in here, we simulated as if the temperature, the atmosphere is increasing from 25 to 36 degrees in these, what is it, like 4 months, okay? And then the advantage becomes even clearer, because under hot environments, if there's no osmotic adjustment, the plant has constantly to close its stomata. So one possible advantage, and it can kind of explain why plants from the tropics don't really do this osmotic adjustment, is that it's good for changing temperatures, right? If there's a seasonal increase in temperatures, and then maybe that's the advantage. I'm really not sure about this because we haven't modeled or think about the below ground. And it could be that osmotic adjustment is important for root exploration or something like that. It was hypothesized in the past, and it's not part of our model. Now, the last thing I want to show you, and it's a very newly accepted paper by Yael Wagner and Kunfung, a PhD student and a postdoc. And basically, these are the researchers. And basically, we wanted to see cavitation with our sensors in a real forest, not just doing the lab simulations or take our data from the lab and apply it to the forest. So we installed our sensors, our cameras, basically. We constantly image this time the shoots of Aleppo pines. This is in Yatir forest. And you see that when you constantly image the shoots, you frequently see funny stuff. So these are the sensors. It's not very clear here at the back. Okay, and basically, every 5 minutes it takes image of the xylem. And then by image analysis, again, because of the refraction of light, we can see where cavitation occurred. And first of all, we did not find a lot of cavitation last year. Only 2 out of our 4 sensors worked throughout the season. So you can see they measured about 10% cavitation. And we also did micro CT once a month just to have a reference. We brought shoots to the lab. And in those shoots, we got about 14%. So overall, on average, we got 12. It's a relatively low percent of cavitation in the forest. And you can see that 2021 was a relatively wet year. Okay. You can see it's based on, in the x-axis, it's the soil water content. So there's relatively a lot of average amount of water in the soil last year. And there was not particularly high VPD during last year. It was a kind of a mild summer. You can see 2015 is marked in yellow because there was a crazy amount of days with high VPD, like 60 days with VPD over 5. And at that year, there was a large mortality event, okay? Even though the soil was it wasn't the driest years in terms of soil, but it was the driest years in terms of atmosphere. Now, we also measure the water potential once a month and the soil water content and the VPD. You can see that the stem water potential was lowest at August during one fairly long heat wave. There was like 5 hot days. You can see it right here. And this is also the period when we saw most of the cavitation events taking place. Because we had, and this is, by the way, the first observation ever of cavitation through time. No one knew when it takes place. Okay, people measured it before a heat wave and after heat wave, but no one can tell if it happened during the heat wave or in the last minute of it or something like that. So we were able to tell when cavitation events occurred. Clearly, they all happened in the middle of the day. Like 77% were between 10 and 4 o'clock, and virtually all of them were in daylight hours. Okay. And we calculated the probability of a cavitation event based on VPD. So in low VPD, you can see that we found like 24 events out of more than 3,000 hours. Very low probability. But if we go to the very high VPD, like over 5, then we had 13 events only in 31 hours. So there was a very high probability for a cavitation event to take place when there's a high VPD. So this is actually the first data ever to directly support the fact that high VPD leads to xylem cavitation. That's it. I'll just give you some take-home message. So first of all, there's the seasonal plasticity of xylem vulnerability is more common than currently perceived. People don't think it changed. It does change. There are also papers in the past, but we added 3 new researches that shows that it happens, and I think soon it will become something that people consider when they do their measurements. if you ignore it, you could conclude that there's a lot more cavitation than there actually is. We don't think that high rates of cavitation are common. It might happen in years of exceptionally high VPD, for example, in dry areas. And that's it. I should thank, first of all, the collaborators here is Shai Netzer, Tamir Klein, Shabtai Cohen, and Jose Carlos Herrera. This is the big lab. We are much smaller these days, but this is the picture I have. So in this project, keep the picture, exactly. Was Jonathan Sorek, Fung Fung, and Yael Wagner. We get money from these guys. So thank you. Shoot.
May I?
Yep.
I want to ask about the same cut also for the federal discussion. I remember that there's a gray or black areas where on the upper circle and then the center. Well, okay.
So cavitation occurs in the
Yeah,
center
so I
and the
understand.
periphery.
No. So xylem cavitation, as the name suggests, happens in the xylem. Okay, there's no cavitation.
Not that one.
Oh, sorry. There's no cavitation in living cells because living cells operate under pressure.
No.
Yeah, I will find it. Don't worry. Yeah,
Oh.
Yeah.
Yes.
So living cells, they operate under pressure. Okay, and therefore they will not cavitate. Even if you punch a hole in them, they will not cavitate. They will simply dry. Okay. Cavitation again is the transformation of liquid to gas. Not what you see here are cavities that exist in woody tissue. Okay, and also here the pith at some trees. You know, when you look at the center, it's actually hollow. It's called the pith. It's not cavitation. The cavitation is something that happens in the xylem. This is the xylem. Okay.
What actually is the black on the bottom? We'll have to look on the.
Yes.
And another question, if I remember correctly, you said if to rehydrate it doesn't happen. It's possible to rehydrate.
The xylem.
Yeah.
It's a question under debate. People thought that it's possible. Most recent studies suggest that most of these studies were, or the conclusions were made by artifacts. There's very little evidence to support quick xylem refilling. Okay.
Is it because it's quickly dead or something else?
I don't know. I just submitted a GIF about that 2 weeks ago, but some species can refill. I know good evidence to support that grapes can refill under specific condition, and that corn can refill under specific condition, perhaps also bamboo. There's not a lot of evidence for many species. The evidence for most species are I think, artifactual. Okay, guy.
Well, excuse my ignorance, just trying to clarify for myself. You said that the cavities are basically when you look at changes from fluid to gas, and now you talk also about embolism, which is basically air bubbles, right?
So
what is?
Yeah, I should have made maybe the introduction, but I already did it.
Yeah, but
so many. Yeah, it's fine.
I'm not that young, so.
Yeah, it's fine. So we're talking about the xylem. Okay, these cavities, there's air spaces all around. The leaf has a lot of air spaces. Most wood has air spaces, even when it's completely fresh. If you throw it at sea, it floats. Yeah, it's not very dense. It has air. It has nothing to do with cavitation or with embolism. Xylem cavitation is when the pressure is very low. Okay, it's called the mechanism called air seeding. There is a bubble that passes through the pits and nucleates the transformation from liquid to gas of the xylem element. So we call that cavitation. It's the function of transformation from liquid to gas. Then when we look at it after, here what we see are the embolisms. Okay, it's the vessels or tracheids in this case. It's a pine that are empty of liquid, that are full of gas. Okay. Cavitation is the function and embolism is the state.
going back to the mechanism. So what has to change physiologically to support the observation that you've shown of the plasticity of this
So we
point of
have many hypotheses, okay, which I don't have proof, but one, the sap can change. Okay, the xylem sap. Now there's some studies about it. It's not all, people thought it's kind of like water. It's not really like water. It has all kinds of attributes. It has surfactants, which change the surface tension, which will change the properties of cavitation. It has some solutes in it. So that could be maybe we tried to look at it and kind of failed. It's very difficult to get a clean sample of the xylem because the concentration of solutes is so.
The xylem or the sap?
Oh, the xylem sap, sorry.
You've shown this droplet from the pressure chamber, right? Yeah, it's easy to extract.
Yeah, so you made a cut to get this, and the concentration of solutes in the cells is about 100 to 1,000 times more concentrated than the sap. So it's very easy to pull that.
You produce more.
Yeah,
solutes.
you create a lot of mass. So it's like, I think a lot of papers that are submitted on this topic are being rejected by the method. That it's very hard to argue that you actually measured only the xylem rather than something that came from other sources. Another possibility is that cell wall, for example, the dead cells can't really change what's inside because they're empty, but cell wall can be built from adjacent cells. There's some recent plant cell papers which show that substrate that coming from adjacent cells can build the cell wall. So even though the cell itself is dead, maybe it is changing its properties by
so it becomes narrower or wider.
Well, narrow and wider is not the thing, but in this paper of Jonathan, I didn't show it to you, but we showed that there is a link between this movement and the thickness of the pit membrane. The pit membrane is a thin membrane that separates between one vessel and one vessel. There is a hole inside the cell wall, but then water has to flow from vessel to vessel, and they flow through a pit membrane. It's a very thin membrane. And the thinner it is, the more vulnerable the xylem element is. So we have showed that it becomes thicker through time. Okay. Yes, but I don't know if it's only that. I have other explanations, but I won't go. It's going to be too long. Okay, Marcel.
About the cavitation, I have a problem I'm trying to think about. I don't have a solution. Maybe you have one. As cavitation occurs, some of the air that's dissolved in the sap is released because it's triggered by some air that comes from the outside. But you have also vapor that is creating water vapor. So you have to have evaporation from
the cavitated vessels.
From the fluid where you have the open air space. If you have evaporation, you need energy.
Wait. Again, sorry. You have cavitation. You have vapor.
You have an air gap inside of the.
Yeah, and in the beginning it's a vapor.
And then you must have evaporation, right? You have to have, because you are in contact with a liquid. You have to have a water vapor escaping from the liquid into the cavity that has been created. In order to have this evaporation.
No. So this is the cavitation. The cavitation, it's the liquid. Yeah, you have water molecules that are connected as a liquid.
Yes.
And because of the tension, they transform to gas. They become the vapor.
Okay, they become vapor. Then you need energy, though.
You meaning it will create some cooling?
Yes, you will have you.
Yeah. Well, there's a lot of energy all around, no?
Yes. So where does the energy come from?
But the leaf has some temperature. It will cool the leaf, I assume, this effect.
So cavitation should cool the leaf.
Yeah, but I assume it's very small amounts of water. I think it's marginal compared with the leaf capacitance. Like it's known to be fairly small. So the leaf is kind of in some kind of a balance with its environment. It's sometimes 3, 4, 5 degrees cooler, but it's not very far from the environment. So I suspect that this effect also doesn't have much of a meaning on the leaf temperature or stem temperature, right? Basically, leaves are poor capacitors. They are always kind of like their environment. It's okay. Huh? Okay.
You don't have cavities in these. These are alive. It's only
The veins, what you see, you know, the veins of the leaf, the veins, borakim.
Okay.
There's xylem elements in these veins. Okay.
Because I'm thinking of cavitation like I boiling water.
Yeah, it will cool. I agree. It will cool the leaf. I just don't think it has much of a meaning to. Danny.
Well, I have a concept how water flows through a plant. I'm not sure exactly, but from what I understand, we have hearts. We pump our living liquid to a pump, and the plant has a mechanism that it has a higher water pressure in the soil near the roots and lower pressure at the stomata. And from what I understand, the elastic part of the xylem is not the part, the stomata, the living part that can shrink or make the lower pressure at the stomata, keeps the gradient upwards towards the leaves. And then when the stomata capacitance goes down, the gradients change, and suddenly you have a lower pressure in the xylem, and the atmosphere wants to go into the plant or whatever.
No, it's not true.
Okay.
The atmosphere is infinitely drier than the plant, almost always. Okay.
Yeah, that's right.
During the day.
Okay.
So even if we are in the tropics at 95% humidity, it will still be, if you make the calculation, I don't know, like 10 megapascal. Okay, the energy of the vapor in the air.
Okay. Yeah.
The plant in the tropics operate at 1. Okay, so the gradient is huge. Now they can open their stomata and transpire more and be at 1.2, and they can close and go down to 0. But always they are, the water moves always to the atmosphere.
So what is when the stomata conductance goes very down and then cavitation occurs? What is the physics of the connection between the collapse of the conduction of the stomata and the cavitation?
So it's not exactly the same. I'm not sure I'm answering the question. It's not. There's not a straight connection.
Huh?
There's not a straight connection. It's not as if I will. You can close the stomata in many ways. Yeah, darkness closes the stomata. There's all kinds of hormones that close the stomata. Closing the stomata doesn't lead to cavitation, unless there is a lot of negative pressure. Yeah, high tension in the xylem. So it only happens if there's a drought. So if there is a drought, typically the plants, what I show you, lose turgor, the guard cells. It's the 2 cells that they are the stomata. They are the stomata pore, more or less. If their turgor goes down, they shut. This is their kind of their mechanism. And when they lose turgor at the same time, also the water potential becomes very negative, and therefore there will be cavitation. But it's not a direct link. It's mediated through the water potential of the tissue.
So the stomata doesn't feel anything from the xylem or.
Oh, of course it does. It feels the water potential. It feeds feeds from it.
I don't think so. I think the stomata are responding only to the rate of photosynthesis. It's completely linked to the process of photosynthesis. Because it's through the process of photosynthesis that the water potential, the cavitation, all these finally affect. I think it's a secondary effect. It's not a direct effect. Because the control of stomata is finally regulated by some biochemical chemical process.
Yeah, but you know you can affect, for example, yeah, if you take a plant and you cut the leaf, you don't change the photosynthesis instantaneously, you know, right?
Oh yes, you change the photosynthesis immediately
Why?
because there is no more supply of water. It impairs.
Ah, okay. So you agree that it's supply of water. Supply of water is the xylem, no?
Yes, but the supply of water doesn't affect directly the stomata. It affects the photosynthesis, and the photosynthesis affects the stomata. In order for the stomata to open or to close, its turgor pressure must be superior to the turgor pressure of the other leaves of the other cells of the
leaf. Yeah.
And as soon as
the thing is, it changed much faster than the photosynthesis. For example, if you cut a leaf, okay,
yes,
the stomata responds immediately in 1 second, okay, or 10 seconds. Immediately, there's what's called the wrong way response. The loss of turgor of the epidermal layer immediately leads to stomal opening. The photosynthesis, if the stomata were open to begin with, it will only change marginally, because the opening from 200 to 300 millimoles is not much of a difference. I can show you data, but it's very easy to change the stomata before you change the photosynthesis. For example, if you put high VPD, a high VPD shock, you don't change the photosynthesis immediately because there's the same light, and to begin with, there's the same stomal opening. But the stomata responds very quickly. I can show you. I can show you measurements. I have measurements.
I don't believe it.
Process of cavity, is it reversible, or once the cavity forms, that's it?
So I told you there's I think only reliable data for the reformation. It's basically refilling, xylem refilling, it's called the phenomena, in maize and in grapes. Probably it happens in many species. It would require, from a physical point of view, you must have positive pressure, right, to dissolve gas bubbles. So plants have positive root pressure, not really at this season, but like a month ago, if you would go early, you see gutation in many of the plants out here. So this gutation is a manifestation for, we call it root pressure. It's the positive pressure of the xylem. So in theory, if there would be a gas bubble inside, it would have dissolved. There's not a lot of evidence to support it, but I think there's just not enough evidence. I believe that it happens. When there's root pressure, there could be xylem refilling, and there is evidence for grapes and for corn.
Take some time to think about the previous answer.
Uh,
I don't remember, you're walking on trees and not annual crops like me. So suppose the membrane thickens.
Mm.
There should be a carryover effect because the cells don't change every year. And if you're talking about a seasonal pattern, then what happens later that year or the following year when you have already thickened membranes?
You mean in evergreen or in perennial crops?
Perennial crops, exactly.
So you are right. So one possibility that it's become thin again. We didn't check it because we did grapes and the leaf is being shed. Yeah, it's one possibility that it's being reversed. Another possibility is it's that actually it doesn't change, but what changes is the creation of new xylem, a new growth ring that then change its properties. And by the way we detected it with the OV sensor, we look mostly on the outer ring. So it will create a larger effect in terms of proportion, because we don't really see what happens maybe to the last year's ring, but definitely not to 4 years back. Yeah, you're right. Toda.
Uri, can I ask you a question?
Yeah.
Great.
Wait.
Okay.
Who is talking?
It's me, Danya, from Rakefet David Swartz Lab.
Yes. איך רואים אותם?
Danya.
Yeah, Tanya, I know you. I just
Yeah.
to see a picture. I don't remember how to do that.
היא בלי תמונה, היא בלי מצלמה.
Okay.
I'm without yeah.
Okay. So ask.
So I have a question about the turgor loss point. Because you're talking mostly about the change in osmolytes over the season and that this is affecting the turgor loss point.
Yes.
And I was wondering about the modulus of elasticity. Like it's also known that the rigidity of the leaves changes over the season. And I was wondering if you observed something like that and what your view is on that. If you also think that this affects the turgor loss point.
So she asked if, you don't care. She asked if also the modulus of elasticity change and not only the turgor loss point throughout the season. So Jonathan found that in most leaves also the modulus of elasticity increased, and it only makes sense if the turgor loss point becomes more negative, then the modulus increase. Yeah.
Okay.
I can share it with you, or Jonathan can show it to you.
But what is the first thing? Is it first the module, like first the rigidity?
What affects what? I don't know. I don't know. There's an analysis of Megan Bartlett, which you can look at from 2012 or 14, and she argues that most of the change in osmotic in turgor loss point is because of solutes. That there's a fairly minor contribution to the bulk modulus of elasticity, but it could be, you know, if you're studying one species, it's not necessarily the case.
Okay. What is this paper?
Bartlett, some analysis of osmotic adjustment. I don't remember if it's in the 2012 or 2014 paper from Lauren Zach lab.
Okay, thanks.
You're welcome. Anyone else from the wide web? Thank you.
תודה.
בשמחה.